These are the notes for day one of implicit differentiation. First, what I want you to do is try the warm-up. Try to find dy dx for both of these functions, then evaluate dy dx at those 2 points for x and see what you get for the slopes of those tangent lines. So after you did the warm-up, hopefully the first one was really easy for you. You get 2 and 8 after you take the derivative, which is 2x. Then you substitute in 1 and you substitute in 4. Now, when you substitute in the derivative into the other one thing that a lot of people are probably going to not get is the fact that you need the plus or minus in front of the square root of x. And that's because this function is actually not a function. That is a relation. And so because that is a relation, you need both the positive and negative halves of that parabola that's going sideways. One thing you'll find out when you graph the relation x equals y squared is that there are 2 points on the graph where x equals 1, and there are 2 points on the graph where x equals 4. So you have 1, 1, and 1, negative 1. Trust me, it's there. I'm having a hard time finding it. There it is. And then you also have 4, 2, and 4, negative 2. And so because there are these 2 points on the graph that exist at each of those x values, you might have more than one slope of the tangent line at those values. So what I want to do is show you these actual tangent lines. You have a slope of 1/2 and a slope of negative 1/2 at the points 1, 1, and 1, negative 1, respectively. And then at the points 4, 2, and 4, negative 2, you have slopes of 1/4 and negative 1/4, respectively. And that should make sense after we take the derivative, keeping in mind that there should be a plus or minus square root of x. Uh, so one thing that we might want to do is be able to find slopes of tangent lines where we're dealing with change in y over change in x. That's what dy dx stands for. One thing we might want to do is find these slopes of tangent lines for graphs that are not necessarily functions of y or functions of x. So what we might want to do then is we might want to deal with a graph, for example, of x to the fourth plus 4xy minus y to the fourth equals 0. So we have a Desmos equivalent of this graph already on our paper. What might we want to do here? What we will do is do something called implicit differentiation, and that can be used when we can't conveniently solve for y in terms of x. So here's an example. We're going to take the derivative of everything. We're going to do 4x to the third. Now, one thing that we haven't really talked about is that when we take the derivative dy dx, whenever we take a derivative of a variable x, we're actually taking the derivative of x with respect to x. Now, just intuitively, we think that the derivative of x with respect to x is going to be 1. And that's because when you change x a certain amount, x is going to change the exact same amount. So we typically don't write dx dx because it ends up being 1. But that's something that happens all the time when we take a derivative with respect to x. That plays an important role as we move along in this. Now let's take the derivative of 4xy. We're going to use a product rule here because both of these are variables in this case. A lot of times when we have two letters multiplied together, we treat one as a constant. In this case, both are going to be variables. So we're going to do product rule. 4, and the derivative of x is dx dx, which is really 1, times y, plus 4x. And then the derivative of y with respect to x, we're going to write dy dx. That's what we do every time we take a derivative of y with respect to x, except in this case, we have this y that's integrated with everything else. Minus y to the fourth, that's going to be 4y cubed dy dx. Anytime you take a derivative of y with respect to x, you write dy dx, and that equals 0. So now this is what our derivative looks like. We want to find dy dx. So if we want to find dy dx, our objective is going to be to get everything on one side that doesn't have a dy dx, keep everything on the same side that has a dy dx. So I'm going to subtract 4x cubed and 4y over to the other side. Now I'm going to factor out a dy dx. And then I can divide everything by 4x minus 4y cubed. And this is dy dx. So what I just found is the slope of the tangent line at any point where you have an x comma y. If you find an x comma y on this graph, what you can do is you can substitute x and y into this and you'll find dy dx. Let's think about it. Why is dy dx in terms of both x and y? Well, that's because there's a lot of different stuff going on. We have a lot of different things going on the graph. We have multiple different values where x and y actually could make this work. The slope of y with respect to x is going to depend on both x and y. So with implicit differentiation, this can be used when we can't conveniently solve for y in terms of x. Here's the process. Step 1, differentiate both sides of the equation with respect to x. So that's being dy dx when you're taking a derivative of y, and doing dx dx, which is really just like putting 1 when you take a derivative with respect to x of a variable x. Number 2, collect the terms of dy dx on one side and put everything else on the other side. Step 3, factor out dy dx. Step 4, solve for dy dx. All right, let's take a look at the function that we looked at originally when we solved for y and then we had to remember the plus or minus and everything else. So if we do this with implicit differentiation, this might actually be easier. So let's find dy dx. I'll take the derivative of y squared. If I'm doing dy dx there, that's 2y dy dx. And then the derivative of x with respect to x is 1. I could write dx dx because that is basically what's happening, but remember dx dx is really just 1. Now, if I want to solve, I can get dy dx equals 1 over 2y. Notice what y is. Y, if we solved, was really plus or minus square root of x. So essentially what I'm getting is exactly the same thing that I originally got, okay? So if I substituted plus or minus root x in here, I would get exactly what I originally got, which is plus or minus 1 over 2 root x, or plus or minus 1/2 x to the negative 1/2. I would have got the same thing. But it's way easier to do this problem as an implicit problem, because now what happens is if I take this as my dy dx, what I can do is I can look at all of my y values where y squared is equal to x, and then I can get appropriate answers. So if I'm trying to find what x is, so for example, earlier we had when x equals 1 and x equals 4. This question isn't asking for that, but if I have a situation like this, I can look at where x equals 1 equals y squared. Well, what's going to be my values for y? Y equals plus or minus 1. And if I take those values and I substitute it into my dy dx, I still get dy dx at x equals 1 of the function y squared equals x is going to be 1/2 and negative 1/2. So I'm still going to get the same stuff, except this ends up being a little bit easier sometimes. Here's another example. Find dy dx for x equals cosine y. So this function would kind of be a little bit of a nightmare. You'd have an inverse trig function, which we haven't learned yet, if you solve it for y. Instead, let's just do dy dx. The derivative of x with respect to x is just 1. And the derivative of cosine of y is going to be negative sine of y dy dx. Now I solve for I solve for dy dx, I divide everything by negative sine of y. And that's what I get. Another example, find dy dx for xy squared minus yx squared equals 20. So here we go. Looks like we have a couple product rules that we're going to do. Derivative of x is 1 times y squared, plus the derivative of y squared is 2y dy dx times x, which was which was the actual function that we had first, or not function, function's a bad word, the original variable that's kind of over there, minus another product rule. So dy dx times x squared plus y times 2x. So 2yx, that's written horribly. This smartboard is not very good at that. Then that would be dx dx. The derivative of 20 is 0 with dy dx. So now I'm going to collect all of my dy dx terms on one side. And then I'm going to subtract the y squared over, and I'm going to add the 2xy over, because if I distributed, that would be a negative 2xy, and then I would add it over to the other side. Now I will finally factor out 2xy minus x squared, factor out a dy dx from those things. And my final answer will be negative y squared plus 2xy over 2xy minus x squared. The next problem that we're going to do is finding d squared y over dx squared of 2x cubed minus 3y squared equals 8. This is really taking the second derivative. So what we're going to do is we're going to take one derivative, and then we'll take the derivative of the derivative. So 6x squared minus 6y dy dx equals 0. We will then solve for dy dx. So we get 6x squared equals 6y dy dx, and then divide through, and we get x squared over y equals dy dx. We will then take the second derivative. So if we take the derivative of dy dx, that becomes d squared y over dx squared. What that really means is we're taking the second derivative of y with respect to x twice. So when we do that, we will have to do the quotient rule. So the derivative of x squared is 2x times the denominator, which is y, minus the derivative of the denominator, which is dy dx, times the numerator, all over the denominator squared. So you end up with d squared y over dx squared equals 2xy minus x squared dy dx, all over y squared. Now what you end up having here is, notice you have a dy dx inside of your d squared y over dx squared. That happens a lot, happens very commonly. If this is a multiple choice question on the AP exam, they will not have your answer looking like this. So you will have to substitute x squared y in where dy dx was. So let's practice doing that a little bit. D squared y over dx squared equals 2xy minus x squared times the other x squared is x to the fourth over y, all over y squared. And we're still going to have to do a little bit of simplification. So we'll multiply the entire numerator and denominator all by y. So then multiplying by y over y is really multiplying by 1. So we have 2x y squared minus x to the fourth all over y cubed. So that's our d squared y over dx squared. We're going to find the equation of the line tangent to x squared minus y squared equals 1 at root 2 comma 1. So we will find the derivative of y with respect to x, 2x dx dx, which we don't really need, minus 2y dy dx equals 0, since the derivative of 1 is 0. Now we're going to substitute in root 2 for x. So 2 root 2 minus, we're going to substitute 1 in for y. So that's 2 dy dx equals 0. Get dy dx all by itself. So we have 2 root 2 equals 2 dy dx. Divide by 2, we get dy dx equals root 2. That's the slope of the tangent line at root 2 comma 1. So if we write the equation of the tangent line, notice that our slope is root 2. If we want the equation of the tangent line, it's y minus 1 equals root 2 times x minus root 2. I want you guys to try this one by yourselves, and then I'm going to put the answer up. So the first thing we're going to do is we're going to take the derivative of this. So we do the dy dx thing, we get all the dy dx parts on one side, and we factor them out. And then we take all of the parts that don't have dy dx, we move them to the other side. Then we divide. So we have 3x squared y minus y cubed over 3x y squared minus x cubed. We substitute in 2 comma 3, and I got 9 over 46. I double checked it, but I've been known to make some algebra or substitution mistakes, so you might want to double check that. And if I screwed up, let me know. So then we have tangent and normal equations listed below.